Welcome back to another episode of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
I'm your host for this summer, filling in for Andrew Dunkley. My name is Heidi Campo, and joining us is Professor Fred Watson, astronomer at large.
Good to be here, Heidi, as always. And you're also our host for this winter here in Australia. So, yeah, lovely to talk. And I think we've got some pretty great questions from our listeners for this episode.
We do. We have some really fun not episodes. We have some fun questions. Our first question today is Martin's from Latvia. And here is his question.
Hello, guys. It's Martins from Latvia. Been loving your show. Been listening since 2017. And so I have a question about dark matter. Okay, just kidding. I have a question about speed of light. So we have two objects. One object is on Earth, and the other one is traveling in space at the speed of light. After some time, it comes back, and the object that's on Earth is older than the other object. So why is that happening again? Why they aren't the same age? I mean, yeah, there's something to do probably when you're reaching speed of light, that time is slowing down or something. But why it's slowing down? Why isn't it just curious. And and I have some dad joke for your arsenal, Andrew. So how do you put a space baby to sleep? You rock it. So anyways, guys, cheers and have a good one.
Well, I think those space babies will be doing well with those jokes. Thank you so much, Martins. That was a good one.
Yep. Space babies always need to be rocked. That's right. So now that's a great question. I have visited Latvia, actually. Some years ago, we did a tour there. I do remember, you know, Heidi, because we've talked about it before. I'm very fond of trains. We traveled on a little railway through the snow and through, because we always visit these places in winter, through snow and woodlands. And it trundled along at something like 9 miles an hour, maybe. It was a fast walking pace because it was a very old line, but it was a lot of fun. Anyway, enough about Latvia. Let's get to the speed of light, which is basically what Martin's question is about. It's one of the fundamental aspects of relativity. Einstein's two theories of relativity, one was about motion, the other was about gravity. It's the one about motion that covers this. That's called the special theory of relativity, dated 1905. And it turns out that the thinking that Einstein had leading up to this was that we know that the speed of light is a bizarre quantity because in a vacuum, it's always the same. We know also that it's the maximum speed that anything can attain. In fact, you can't actually achieve the speed of light with an object because you would have to put infinite energy in to get it to the speed of light, and we don't have infinite energy. So light and its other electromagnetic waves, they are the only things that can travel at the speed of light. But if you had something that you are accelerating, well, let me just go back. The speed of light is it's almost like a magic number. It's not magic because it's a very round number. It's about 300,000 kilometers per second. It is, however, the fact that it doesn't change in a vacuum. And it doesn't matter how fast the source is moving. You'd expect if you have a source that's moving that sends out a beam of light, the source's speed would add to the speed of light, and the speed of light would increase. But it doesn't work like that. And once you establish that, then it turns out, and there's some quite sort of simple ways of seeing how this might work, which we don't really have time to talk about, but some of the books about special relativity that talk about people looking at somebody moving on a train show you how the geometry works, that because the speed of light is always the same, then what it tells you is perceptions of time and distance must change. And so the key thing here, and the point that Martins is raising, is that if you've got an observer who is stationary compared with somebody who's moving at a very high speed, nearly at the speed of light, or it doesn't matter whether it's near the speed of light or not. The effect works, but it's when you get nearer the speed of light that it becomes noticeable. The time that you observe that moving person experiencing is slower. So your time's ticking away as normal, and the person who's moving past you, their time is ticking away as normal. But when the stationary person, if you could see the clock on the moving vehicle or whatever it is, train going at nearly the speed of light, just to mix a few metaphors there, what you would see is their clocks would seem to be going much more slowly than yours is. And that's the time dilation effect. And yes, it means that if you can then bring these two back together, the moving person has experienced less time relative to you than you have. And it's sometimes called the twins paradox, because if you take two twins, one goes off at the speed of light, comes back again, or nearly the speed of light, comes back again, they have aged much less than the twin who stayed put. So that's the bottom line, and it's such a counterintuitive concept that it is really hard to get your head around. But we know it works. In fact, the demonstration, the practical demonstration of this phenomenon happening in reality, I think it was just before the Second World War, might have been round about the same time. But there are things called cosmic rays, which are bombarding the Earth all the time. These are subatomic particles that come from space, and they are predominantly a species of subatomic particle called a muon. So these muons were observed coming down through space at nearly the speed of light, and we know how long they take to decay in the laboratory, but their decay time was much longer when they were observed coming in at the speed of light, nearly the speed of light. The time had dilated, so their decays were much longer than what we observe in the laboratory when they're not stationary, but they're going much more slowly. So it is a proven fact. This works. If we could build a spacecraft that would get us to, I can't remember what it is, I think it's 99.99998% of the speed of light, head off for 500 light years, come back again, you will be 10 years older, whereas everybody else on Earth will be 1,000 years older. So it's that sort of thing, your time has slowed down relative to what they've experienced.
I had a weird nightmare about that the other night.
Oh, did you?
It was the strangest thing. I had a nightmare that somebody put me in like some kind of a cryo sleep, and I woke up and so much time had passed that everyone I knew had died. And so I had them put me back in cryo sleep for thousands of more years until we discovered the technology to travel back in time. Okay. So I could go back in time and link back up with everyone I loved.
That's a pretty good. That's a pretty good one, is that?
I have a very active dreamscape at night. I wake up exhausted.
Okay.
All right. Well, our next question has a little bit of philosophy in it. This question is coming from Art from Rochester, New York, and it's quite a long question. So let's grab a cup of tea here. Art says, I was listening to the June 13th program concerning the flying banana, which prompted me to submit my first question to Space Nuts. It is a question I had been pondering for some time. You will be glad to hear it is not a black hole question, but rather a what-if question. The great American philosopher Julius Henry Marx once postulated, time flies like an arrow, fruit flies like a banana. Based on empirical evidence, I can confirm that fruit flies like a banana. My question revolves around time flying like an arrow. To the best of my understanding, when we shoot off rockets to the moon or Pluto, in order to get there accurately, the rocket scientists use an ephemeris, you'll have to correct me on the pronunciations of that, or possible ephemerides as a sort of a map. If faster than light space travel were possible, how could one navigate from point A to point B? Is it possible to develop an ephemeris for faster than light travel? Thank you, Art from Rochester, New York.
A great question, Art. And your pronunciation is correct. Ephemeris is what these things are, and ephemerides is what a lot of them are. So what's an ephemeris? Well, the original meaning, and I guess this really is still the meaning of the word, is to predict where planets are going to be in the future, where celestial objects are going to be. So going back to my master's degree, back 150 years ago, my work was on the orbits of asteroids. And so there were two problems. First problem was, how do you take observations of an asteroid? And remember, all we had in those days was the direction that you could see measured with a telescope. How do you turn that into knowledge of the orbit of the asteroid in 3 dimensions? And you can do it. You need at least 3 observations to do that, but you can do it. You can mathematically deduce the orbit from just 3 directions in space. But then once you've got the orbit, what you want to know is where it's going to be in the future. What's its direction in space going to be? And that is what an ephemeris is. It's how the position of an object changes in the sky over time. So it comes from the word ephemeral, meaning stuff that's temporary. So an ephemeris is the basically it's a table of where an object will be over a given amount of time. And of course, it's critically important these days, because we now know that, which we didn't know when I did my master's degree, we now know that the Earth's locality is pretty heavily populated with asteroids, and there's, we might want to know where they are, just in case one's heading our way. So I think Art's question is a good one, in the sense that, okay, he's saying, yes, we use ephemerides to basically navigate to objects. It's actually a little bit more than that, because we use effectively a 3-dimensional map of where these planets are in order to dictate where they're going to be when your rocket arrives there. And that's critically important, of course, because you want the rocket to get to the orbit of, for example, Pluto, as Art mentions, when Pluto is going to be whereabouts the rocket is. You don't want to reach the orbit of Pluto and find Pluto somewhere else. That's why you need an ephemeris. But if you could travel faster than the speed of light, and we've already shown that that's impossible in this episode, because you need infinite energy to do that, to reach the speed of light. But if you could, the ephemeris would still work. You would need to put in a negative number for the I think the speed of light goes into ephemeris calculations. I remember it well, but I think you put in a factor. It wouldn't be a negative number. It would be a factor that would allow for the fact that you were traveling at faster than the speed of light. So you could do it. It's not an impossible mathematical problem, for what it's worth.
Well, that was fantastic. I just about understood that too.
Sorry.
You always do such a great job of explaining these. My IQ is going up every time I'm involved on these episodes, and also great questions. We have some of the smartest listeners. I mean, these people are brilliant.
Let's take a break from the show to tell you about our sponsor, NordVPN. And we're very proud to have partnered with NordVPN so that we can get you more secure online, no matter what you do, where you are, or how you do it. Now, if you sign up for a 2-year NordVPN plan using the code word SpaceNuts, you'll receive 4 extra months absolutely free. That's 28 months of top-tier VPN protection at a fraction of the cost. With NordVPN, what you get is access to over 7,700 servers worldwide, ultra-fast connections, advanced features like Threat Protection Pro and MeshNet, and secure usage for up to 10 devices simultaneously. So you're pretty well covered, you have to admit. Now, this is a great opportunity, and if you'd like to take advantage of it, visit nordvpn.com/spacenuts to claim your exclusive offer today. And remember, with NordVPN's 30-day money-back guarantee, it's risk-free. It's a great investment, a small price to pay for your online security and privacy. Stay secure, stay connected, and keep exploring the cosmos with confidence. nordvpn.com/spacenuts, nordvpn.com/spacenuts, and don't forget the code word spacenuts at the checkout. Now, back to the show.
Roger, you're loud and clear here also.
Space nuts.
Our next question is another audio question from David from Munich. And it's a little bit of a longer question as well. So we are going to go ahead and play that for you now.
Hey guys, David from Munich here. Shout out to Andrew, Fred, and John T. And I heard that you're a bit short on questions, so I thought that's my chance to submit one. I'm currently looking at the picture taken by the James Webb Telescope. You know, the first one, the first deep space, which was also presented by President Biden back then. And I realized that the galaxies do differ in their color pretty much. So there are more white ones, orange ones, and also reddish ones. And I wonder, how is that? Is it due to the fact that, or is this like the redshift because they're moving away? Which I kind of doubt, but I don't know what is it else, or is there so much material of a different kind in the galaxy that it appears for us more red or more blue? So it would be nice if you could explain that. And also, I wonder a bit. Let's imagine we would travel to this far distant galaxies, if we could do it potentially. Would it not be some kind of travel through the time? So because when we look back there, right, we see them on their early stages. So till it's a long time till their light reaches us. And if you would travel to that far distant galaxies, you would basically, or what I imagine is like you would travel through time, right? So if the moment you come closer and closer, the galaxy, or maybe let's think of a single planet, would then change its appearance, right? So you would see that it's altered, it shifts maybe its base, or it merges with another galaxy. Is my thinking correct? Would it like the closer you come, the more it would change its shape, and it's, I don't know, colors maybe, and things you would see. Thanks for taking my questions. Like the show, and till then.
Well, thank you so much. That was David from Munich. Thank you. That was a well thought out question. Fred, I'm so curious.
They were great questions, Heidi, from David. And in fact, the answer to both his questions is yes. So David's asking whether the color changes that we see in the images of these deep fields, as we call them, looking way back in time, whether those different colors of galaxies is caused by the different redshifts of these galaxies. And that's the bottom line. But there's a few caveats here. Let me just explain what I mean. Redshift is the phenomenon that as light travels through an expanding universe, the universe is expanding, light is making its way through the universe, but as it goes, the universe is getting bigger, and so the light's wavelength is actually being stretched. And as you stretch the wavelength of light, it goes redder. It goes to the redder end of the spectrum. And so that's what's happening. But the caveat that I mentioned is that these are actually false colors, in the sense that the James Webb Telescope is an infrared telescope. So it is looking at light that our eyes are not sensitive to. It's actually redder than red light that it's looking at. So what the mission scientists do is they take the shortest wavelengths that the Webb can see, which are really beyond they're redder than red for us, for our eyes, but they're the shortest wavelengths that the red can detect. And they make that blue in their colors. And then the longest wavelengths that the Webb can detect, they make it red in their colors. And that mimics what we would see with our eyes or with visible light, but it mimics it moved into the infrared. So it does mean that as objects, get redder in the infrared spectrum, we see them redder in the James Webb Telescope images. And that's exactly the reason. The most distant objects are so highly redshifted that you're seeing them as red objects compared with the white objects, which are the much nearer ones. So David's right on that front. His second question, what would some of these galaxies, we're looking back, up to, I think the record is looking back 13.52 billion years at the moment, which is 280 million years after the birth of the universe. It's a big puzzle as to how galaxies got so big and so rich in that short period of time, but that's for the cosmologists, not for us. They'll work it out. It'll be okay. The bottom line, though, is that if you could forget about the journey, because we can't travel the sort of speeds that you need, but if you imagine yourself instantly transported from our vantage point here on Earth to one of these early galaxies, 13.52 billion light years away, what you would see would be a galaxy that might look a lot like ours. It has evolved because you're seeing it. I mean, you've got to imagine we're being transported instantaneously, so that what we see is what's happening now. That galaxy will have had 13.52 billion years of evolution. It'll be quite different. It might actually be quite a boring galaxy compared with the very energetic infant galaxy that we look at with the James Webb Telescope. Complicated answer to a simple question, but David's right on the money.
That is such an interesting way of thinking about that. I'm going to be spending a while wrapping my head around that one.
Okay, we checked all 4 systems and skiing with a go.
Space Nuts.
Our last question of the evening is from Daryl Parker of South Australia. Daryl says, "G'day, Space Nuts. I'm not sure of the best way to ask this question, so I'll just ask it the best way I can." That's usually the best way. Do objects, meteors, asteroids, comets, planets, stars, solar systems, and galaxies produce heat as they move through space? Is it friction, or is friction a thing in the vacuum of space? Thank you in advance. And that's Daryl from South Australia.
Another great question. So if space was a complete vacuum, and as I'll explain in a minute, it's not quite, but if it was a perfect vacuum with nothing in there, then there would be no friction, as Daryl's calling it. It would be, there'd be nothing to limit the speed of motion of an object moving through it, and it wouldn't get hot. There would be no friction to heat it. And I think the way Daryl's thinking here, and it's quite right too, when a spacecraft enters the Earth's atmosphere, it's the friction between the spacecraft itself moving against the air molecules that causes it to be heated and gives us this heat of re-entry. There are a few subtleties of that, but that's basically the way it works. So things moving through an atmosphere get hot. Now, into space beyond the Earth's atmosphere is not a vacuum. It's very nearly a vacuum, and that's why you can put a satellite up and it'll stay up for 200 years or whatever. And it's why, the moon doesn't come crashing down to Earth. In fact, the moon's going the other way. It's moving away from the Earth very slowly. But it's nearly a vacuum, but it's not quite. So there is basically a very, very slight braking effect, which in the Earth's vicinity, the Earth's atmosphere doesn't just stop, it sort of fades away. So even 10,000 kilometers away, there's still a little bit of residual atmosphere, which would have a slowing effect on a spacecraft. When you get into interplanetary space, there's a lot of dust, and there's also subatomic particles there. When you get to interstellar space, the space between the stars, there is something that we call the interstellar medium, which is basically the radiation and particle environment of interstellar space. There are subatomic particles all through space. Now, it's still so much of a vacuum that there's nothing really to heat a spacecraft. So Voyager, as it ventures through interstellar space, it is on the brink of interstellar space now, that won't get hot because of that, because the friction is far too small. But when you do see its effects, they are on very big scales. And we do see, when we look at some objects deep in space, for example, in a gas cloud, a nebula, where maybe there are stars forming. Sometimes you see objects which are moving through that gas cloud, and what you can see is a shock wave being generated, and sometimes that causes star formation, that shock wave of the gas cloud. Now, yes, that's Geordie agreeing with me there. He's just come back from his walk, so he's very enthusiastic about this idea. He's probably seen a shock wave. So, and a shock wave is what you get when something moves rapidly through the atmosphere. That's what causes the sonic boom of a supersonic jet. So with very big objects, in gas clouds in space, then you do get that sort of effect. The interaction between the moving object and its surroundings generates a shockwave and would generate heat as well. So under certain circumstances, the answer is yes, Daryl, but probably for most things, it's no.
So Fred, I don't know if you'd have time for a follow-up question.
Yes, of course,
of my own.
Yes,
of my
absolutely.
own. So I guess I never really thought of the gravity atmosphere around planets having different layers. It's like I knew there was layers, but it's like to really think, okay, it gets thinner and thinner and thinner, but there's still particles being pulled into that atmosphere, but it spreads out quite a ways, well beyond our atmosphere. Are there points of space, and you may have already mentioned this, but are there points of space where there's particles floating around that are not being affected by any gravity at all? Or is every part of space affected by something's gravity?
Yes, pretty well. The thing about gravity is it goes on for infinity. It's a bit like, actually, light is the same. Electromagnetic radiation will not stop; it just keeps going and until it gets too weak to be detected. And you're talking about a dribble of hardly any photons. Gravity is the same. We don't know whether gravity has a subatomic particle equivalent. We think it might have, and we call them gravitons, but they haven't been discovered yet. But yes, that's actually, it's why an object like Pluto, way out there in the depths of the solar system, is still in orbit around the sun, even though it's all these, 5-6 billion kilometers away. The gravity of the sun is still a force because gravity goes on forever. But of course, when you get way out into interstellar space, then you might feel the sun's gravity, but you'd also feel the gravity of other stars. And so I think you're right that there is always going to be a sort of gravity background because of the objects which are in the universe. Maybe it's pretty near zero in the space between galaxies, which is pretty empty, although there are subatomic particles there too. Right. But no, it's a very compelling force is gravity, which is just as well, because otherwise we wouldn't exist.
There's always something pulling. It's just going to be stronger or weaker. No matter if it's the biggest gap in the known cosmos. There's still a little thread pulling us together. Oh, that's so beautiful. That's kind of cool. We're all connected somehow.
That's a connection. That's right. Yeah.
Fred, well, this has been a very enlightening Q&A episode of Space Nuts. Thank you so much for sharing your wealth of knowledge with us while your dog sings his song in the background.
That's what he sounds like. I know it's his voice hasn't broken yet.
It's kind of cute. It's endearing. Yeah. Thank you so much. This has been fantastic, and we will I guess catch you guys next time. Please keep sending in your amazing questions. And real quick before we go, we are going to play another another update for you. So this is your little treat for listening to the whole thing. We've got an update from Andrew, your beloved regular host. I know you guys probably miss him because your questions are still addressed to him, but he's on his trip around the world. So we're going to let that that play back now.
Hi, Fred. Hi, Heidi. And hello, Hugh in the studio. Andrew back again, reporting from the Crown Princess on our world tour. Since I spoke to you last, our cruise has made news all over Australia. You might have seen some of the reports or heard some of the news about some of the conditions we've had to deal with. When I last spoke to you, I was explaining how we were heading into rough weather. We got off to a pretty rocky start. Well, it got much, much worse. We were having lunch in one of the restaurants at the back of the ship, and we got hit by a weather front. It felt like we'd been rammed, and the ship tilted over 7 degrees, and it stayed there for the rest of the day. It just hit us out of nowhere. The captain had to do some heavy manoeuvring to get us into a better position, and they had to move the ballast to keep the ship balanced and upright as much as they could. It was pretty harrowing, and the weather never got better until we got into Adelaide and were in protected waters. But Adelaide was fantastic. Went to Handorf, as I mentioned, that little German village where the German people came in all those years ago. They were basically escaping Prussian oppression when they came out here in the 1800s, and made a German town, which is fantastic. Had a good look around Adelaide, although the weather was terrible. We went to Mount Lofty, which is one of the best views in Australia, and all we saw was cloud and very strong winds. It was quite nasty. Got back on board. We had to stay the night in Adelaide because of the conditions, hoping they'd settle down, and we did have some good sailing until we got to the West Australian border, and then another weather front hit us and it got rough again. And just to top it all off, we had a galley fire in the middle of the night at one point, which they dealt with very, very quickly. So it's been a bit of a dog's breakfast of a cruise in some respects, but we're still having a fantastic time. We stopped at Fremantle again. Because of the weather, we were very late, and so we stayed the night. We have friends in Fremantle, so we spent the evening with them. It was fantastic. And we set sail again yesterday, headed west. We leave Australia now, headed for Mauritius. That'll be a 7-day crossing of the Indian Ocean. So that's where things are at with our current tour. We're really enjoying ourselves. I must confess, the crew here is fantastic, and with over 2,000 Aussies on board, we outnumber everybody about 10 to 1, which is which is good. But so many nationalities. Hope all is well back home, and in Houston, of course. Heidi, look forward to talking to you next time. No Aurora Australis, missed out completely, couldn't see that. So hopefully when we get up north, we'll see the other end of the country and see if there's any lights up north. So until next time, Andrew Dunkley signing off.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favourite podcast player. You can also stream on demand at Bytes.com. This has been another quality podcast production from Bytes.com.
See you later, Fred.
Sounds great.